Everything around us is constantly moving, from the cars on the street to the planet we're standing on. But to really truly understand it all, we need to speak its language. So today, we're going to learn the vocabulary of physics, a super precise way to describe something as simple as moving in a straight line. It's kind of like the hidden language that runs the universe.
Look, we all know what fast or far means, right? But in physics, our everyday words, well, they just don't cut it. They're not specific enough. So how do we build a language that's crystal clear about motion? That is exactly what we're going to figure out together.
All right, so let's start at the very beginning, the absolute fundamentals. I mean, before we can even get into how fast something's moving, we have to agree on two simple things: where it is and how far it's gone.
Think about it for a second. You can't just say an object is at 5 meters. 5 meters from what? Is that 5 meters to the right of the door or 5 meters to the left? See? That's why, to define position, we always need two things: a starting point, what physicists call the origin, and a clear direction.
So, this brings us to our first big, really important idea in physics, the difference between distance and displacement. Just think of distance like the odometer in your car. It just racks up the miles, right? It only ever goes up. Displacement, though, it's a whole different animal. It's just the straight line change from where you started to where you ended. And for displacement, direction is everything.
And here's where that difference becomes so obvious. Let's say you walk 5 meters forward, then turn around and walk 5 meters back. The total distance you walked is 10 meters. Your legs are tired, for sure, but because you ended up exactly where you started, your overall change in position, your displacement, is 0. As far as physics is concerned, you haven't gone anywhere at all.
Okay, so we've nailed down how to describe where something is. The next logical step, then, is to describe how fast it's moving from one place to another. This is where we start to add some action to our new language. Average speed is something we all kind of get, right? If you drove 100 miles in 2 hours, your average speed was 50 miles per hour. It's a really simple calculation, just the total distance you covered divided by how long it took you. It gives you a nice, simple, big picture idea of your pace.
But here's where our new physics language gets way more powerful. Average velocity uses displacement, not distance. And what does that mean? It means it doesn't just tell you how fast you were going, it tells you how fast your position was changing and in which direction. That direction, that's the crucial upgrade.
Okay, let me ask you something. Based on what we've just talked about, is it actually possible to be moving to have an average speed that's not 0, but at the same time have an average velocity that is 0? What do you think? Yup, you absolutely can. The running track is the perfect example. Let's say you run a 400-meter lap in 60 seconds. You definitely had an average speed, but since you finished in the exact same spot you started, your displacement is 0. And if your displacement is 0, well, your average velocity has to be 0 too.
So we've got position, and we've got how that position changes over time. But motion usually has a plot twist. Things rarely just move at a perfectly steady speed forever. We need a word for that change, and that word is acceleration.
Now here's the official definition, and I want you to pay really close attention to one specific word here: velocity. Acceleration isn't just about how fast you're going, it's about how fast your velocity is changing. It sounds like a small difference, but trust me, it is a huge deal.
And this is where a lot of people get tripped up. We think acceleration just means hitting the gas. But in physics, hitting the brakes is also a type of acceleration. We just call it negative acceleration. And get this, even turning a corner while your speedometer stays the same, that's acceleration too. Why? Because your direction is changing, and direction is part of velocity.
So we have all these new terms flying around: displacement, velocity, acceleration, but how do we see the entire story of an object's motion all at once? Well, for that, we need to unlock the physicist's secret weapon.
Yeah, forget reading long paragraphs or staring at tables full of numbers. A simple graph can tell you everything you need to know about a journey. Where it was, how fast it was going, if it was accelerating, all in one clean, elegant picture. Okay, if you only remember one thing from this whole explainer, please make it this right here. This is the golden rule. It is the master key for reading any motion graph. The steepness of the line, the slope, tells you about a rate of change. And the area underneath that line, that tells you about a total amount. Let's see how our golden rule works. So, on a position versus time graph, the slope tells you the rate of change of position, which is just velocity. Simple.
Now look at a velocity versus time graph. The slope is the rate of change of velocity. Hey, that's acceleration. And the area under that line? That gives you the total displacement. See how it all just clicks together? It's pretty cool.
I know this has all been a little abstract, so let's bring this all back down to earth. How does this fancy new language actually help us describe something we see every single day? It's time to put all our new tools to work.
A car driving through city traffic is the perfect real-world example. Its motion is messy, right? It speeds up, it cruises for a bit, it slows down, its acceleration is changing all the time. But even with all that complexity, our new language gives us the tools to describe exactly what's going on.
So let's tell the story of a car going from one stoplight to the next. First, you hit the gas and pull away. That's positive acceleration. Then, for a few seconds, you're cruising at a steady speed. Your velocity is constant, which means you have zero acceleration. And finally, you see the next red light and hit the brakes, and that's negative acceleration. We can now describe that entire sequence perfectly.
And here's one last really powerful idea for you. Motion is always relative. When you pass a car on the highway that's going the same direction, it feels like you're barely moving past them. But when a car comes at you from the opposite direction, whoosh, the speed feels huge. What we see and what we feel always depends on our own point of view.
All right, let's do a quick recap of our new vocabulary. We started with position, just where you are. That led us to displacement and velocity, which are all about direction. Then we learned that acceleration is any change in that velocity. And finally, we saw that graphs are the key to telling the entire story of motion.
So you now have the basic tools to describe the world like a physicist. Seriously. So the next time you're in a car or just watching the world go by, ask yourself, what's its velocity? Is it accelerating? Now that you know the language, what story is the motion all around you really telling?